Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper trending on X, published on July 23, 2025, just a few days ago. This paper proposes a way to send a phone-sized payload to interstellar space in less than a year, using only sunlight. The paper is titled, Torqued Accelerator Using Radiation from the Sun for Interstellar Payloads, or TARS for short. And it's a fascinating approach to a classic science fiction problem. It describes a system that stores solar energy as rotation, kind of like a flywheel, before flinging a probe towards the stars. And it's already getting a lot of attention on X, with people pointing out that while it might not be as fast as other proposals like Starshot, it seems far more practical to actually build. The discussion is noting that since the whole system only weighs a few kilograms and uses existing materials, it could be a really accessible technology. There's also some talk about a cool side effect. The magnetic field generated by the spinning system could potentially be used for things like radiation shielding for a future Mars base. Alright, so let's dig into how this system actually works. This initial diagram shows the basic concept. You have two paddles connected by a tether, orbiting the sun. Now the key idea is that each paddle has two different sides. One side is highly reflective, while the other is more absorptive. This difference in what's called albedo, which is just a measure of reflectivity, creates an imbalance in the radiation pressure from the sunlight. This imbalance generates a torque, a gentle but constant twisting force that makes the whole system start to spin up, faster and faster over time. Building on that, this figure shows us a close-up of exactly how that works on one of the paddles. It breaks down the energy fluxes, which is just the amount of power per unit area from the sun. When the sunlight, or insolation, hits the paddle, three things can happen. As the solid lines show, some energy is transmitted straight through, some is reflected, and the rest is absorbed. That absorbed energy is then radiated away as heat, shown by the dashed lines. This detailed energy balance is the core mechanism driving the whole system. Okay, so how long does this gentle push from sunlight actually take to get us going? This table gives us some concrete examples. It shows the time needed to reach 10 kilometers per second, comparing different sails based on their areal density, which is simply their mass per square meter. The three time columns represent different scenarios, with the last one showing a highly eccentric orbit that swings very close to the sun. And the results are remarkable. For a material like Sunjammer, this orbital trick cuts the spin-up time from over a year to just 3 weeks. So, to withstand those incredible rotational forces, the actual shape of the paddle is critical. This figure shows a clever solution called a tapered ribbon design. In the top diagram, you see the paddle isn't one solid piece, but segments that get narrower towards the tip. This is because the tension is highest at the center, so this design saves mass. The bottom diagram shows how they add the payload, replacing the outer tips with a dedicated sail that's made wider. This adds the necessary tensile strength, its ability to resist being pulled apart, ensuring it doesn't break off prematurely. Moving to the results, this plot really brings those design trade-offs into focus. On the horizontal axis, we have a design parameter called K, which basically controls how the payload is integrated into that tapered ribbon. The black line shows us the final velocity. When it's above 0 on the left axis, our probe has enough speed to escape the solar system. But look at the rust-colored line. That's the system's total mass. As you increase K to get more speed, the mass just explodes. The key is finding that sweet spot where the design is stable and just fast enough. So in the end, it's all about that careful balance. This paper presents a really elegant solution, using sunlight to spin up a device and then fling a small probe into interstellar space. It's a promising, low-cost alternative to giant laser arrays, and seems feasible with today's materials for sending out small, sub-relativistic probes. That's it for this episode of the AI Research Roundup. I'm Alex, thanks for listening.